Hello students, welcome you all to another video of our engineering physics series. So here we will discuss about ledger. In this video we will discuss about what is a ledger, how it works, what are the working principle and what are the different phenomena behind working of a ledger. And also we have the construction, structure and working principle of Ruby ledger. First we will discuss about what is a ledger. So ledger stands for light amplification by stimulated emission of radiation. From here you can see light amplification by stimulated emission of radiation. So when the intensity of light is amplified or increased by stimulated emission, normal emission you know that when electron jumps from higher energy state to lower energy state. We will discuss in details about what is stimulated emission. So that phenomenon is known as ledger. So the light produced by any ledger is one directional and highly intense light. So you must have seen the ledger light. Here is a picture. So first we will discuss about what is atomic excitation. Normally you know that in case of any atom, if two energy states are there, E1 and E2, where E1 is the lower energy state, E2 is the higher energy state. So at thermal equilibrium or in equilibrium state, all the particles stay in lower energy state. When some external energy is given, if h nu amount of energy is given to the particle, and that h nu is the difference between E2 minus E1. E2 minus E1 equal to if h nu, then this particle will excite and move to the higher energy state, excited state. So this is known as excitation. But in excitation state, all the particles are always unstable. So they will try to release energy and convert to the ground state. So that is said to be de-excitation process or emission process. So in de-excitation process, the excited particle present in the higher energy state, which is represented by here E2, release some amount of energy and comes back to the ground state. So these are two different methods. One is excitation method, another one is de-excitation method. These two methods are important in working of any ledger. So here you can see it is written when electron receives an amount of energy equal to the difference of energy. Difference we have written E2 minus E1, which is equal to h nu. Then from ground state, that is lower energy state, it will jump to higher energy state, that is said to be excited state. And this phenomenon is said to be excitation process. And in excited state, always the particles are unstable. And generally each electron stays there for 10 to the power minus 8 seconds. 10 to the minus 8. But in some case you will find out that electron stays for a longer period of time in excited state. Those states are said to be metastable state, that is virtually stable state. Here it is, you can see it is written 10 to the minus 3 second, that states are said to be metastable state. So metastable state means what? Now those are also, metastable states are also excited states. But the difference is that in normal excitation state, always particles stay for a short period of time in the range of 10 to the minus 8 second. But in metastable state, particle or the electron stays for a longer period of time as compared to the normal excited state. So that time period is in the range of 10 to the minus 3 second, which is written here, 10 to the minus 3 second. So de-excitation means particle release energy and comes back to the ground state energy. So externally if we apply energy to any atom, then it can interact with the atomic energy levels in three different ways. We are going to discuss that in the next slide. So here you can see the external energy can interact in the phenomenon of absorption, in the phenomenon of spontaneous emission and stimulated emission. This stimulated emission is nothing but where ledger actually activated. That means we get intense light from the source of ledger. So we will discuss about each one of them individually. So externally when we apply energy, it will interact by absorption, by spontaneous emission, by stimulated emission. So first we will discuss about what is absorption process. Already we have discussed if two energy states are there, lower energy state is E1, higher energy state is E2. Then when initially the particle present in the lower energy state, if external energy is given, then the particle will absorb energy and go to the higher energy state E2. This phenomenon is known as absorption process. This is before absorption, and this is after absorption. So when external energy is given to the particle in ground state, it will absorb energy and move to the higher energy state. That phenomenon or that process is known as absorption. So if A is the symbol of the particle, then when h nu amount of energy is given to the particle, A is the symbol and h nu is nothing but the radiation energy or light energy, then it will go to excited state, and all the excited states are represented by a star mark. Here also you can see particle is represented by here, and here represented with an extra star mark. That means it is in excited state. Similarly, in symbol also you can give a star mark in order to represent excited state. Excited state. So this phenomenon is known as absorption. Then rate of absorption. So rate of absorption means how many number of particles are moving from lower energy state. Let N1 and N2. We represent N1 and N2. N1 is number of particles per unit volume present in the lower energy state, and E in energy state E1, and N2 is number of particles present in the higher energy state having energy E2. That is per unit volume always calculated. So rate of absorption means how many number of particles are moving from lower energy state to higher energy state per unit time and per unit volume, because energy density is always calculated per unit volume. So we will discuss that in the next. So your rate of absorption for absorption we have written AB. So rate is nothing but how many number of particles are moving from lower energy state to higher energy state. In lower energy states we have written N1 number of particles. So we can directly write down dN1 by dt. And you can also write down here a negative sign. Negative sign because number of particles gradually, if we see, if N1 number of particles are there, when one particle will go to the higher energy state, now the number of particle will be N1 minus 1. If another particle will move, then it will be N1 minus 2. So gradually you can see the number of particles gradually decreases in the lower energy state, whereas in the higher energy state number of particles gradually increases. For that reason we have given here a negative sign. So negative sign indicates that N1 decreases with respect to time, but you can also represent that in terms of N2 also, dN2 by dt, because N2 gradually increases. Let me explain that here. If 4 number of particles are here, one particle is moving from lower energy state to higher energy state. Now the number of particles remaining is 3. If another particle increases, move from lower to higher, now number of particles is 3 minus 1, that is 2. So gradually you can see initially number of particles was 4, then decreases to 3, now decreases to 2. So N1 always defines number of particles in the lower energy state. So N1 gradually decreases with increase in time. For that reason we have given a negative sign. But here you can see N2 represent the number of particles in the higher energy state. In the ground state, when all the particles are in ground state, number of particles here, let N2. Now the particle will be N2 plus 1, then N2 plus 2. If another particle will jump, N2 plus 3. So number of particles gradually increases in the higher energy state. For that reason here there is no negative sign. N1 decreases with time, N2 increases with time. So here rate of absorption depends upon two factors. One is how many number of particles present in the lower energy state, that is N1. If there are 4 electrons present or 4 particles present, so maximum number of particles can move will be 4, not more than that. So it depends upon how many number of particles, and it also depends upon the amount of energy given, that is energy density. Rho B is nothing but energy density. Energy density means energy by volume. For that reason V is written here. Then how it depends upon energy also. Let each particle or each electron requires h nu amount of energy. So when there are 4 electrons present in the lower energy state, we are giving let h nu amount of energy. So each h nu is responsible to move 1 electron from the lower to higher. So 1 electron will jump. Again, if we are applying 3 h nu of energy, then total 3 electron will move. That means when energy increases, number of particles also increases. The number of particles moving from lower to higher increases. But if we apply 5 electron volt of energy, there are four electrons. So out of 5, 4 h nu amount of energy is responsible to move all the 4 electrons from the lower to higher energy state. So it depends upon how many number of particles present as well as how much external energy is given to the system for excitation process. So it depends upon both number and energy. So if it is proportional, you can directly write down like this: RAB, rate of absorption, is equal to some constant is written here B1 to N1 rho B. B12 is a constant of proportionality and it is known as 1 to 2. Since the particles are moving from lower energy state E1 to higher energy state E2, so it is written from 1 to 2. This is Einstein's coefficient of absorption process. B12. Clear? Then we will go to spontaneous emission. So spontaneous emission means during absorption process, all the particles move from E1 to E2. Let we consider one particle is here. It is in excited state, but in excited state, we know that all the particles are unstable, so they will release energy and return back to the ground state. So it will release some amount of energy and jump to the lower energy state. This is known as spontaneous emission. Spontaneous emission because by its own it will release energy because it is unstable state. So it will release energy and comes back to the ground state. That's why that is said to be spontaneous emission. So rate of spontaneous emission depends upon dN2 by dt. And again here negative sign dN2 by dt. So you can directly write down rate of spontaneous emission equal to minus dN2 by dt. Negative sign indicates that number of particles, if the particles are moving from higher to lower, if 2 particles are there, then gradually number of particles, that is N2 in the higher energy state, gradually decreases. For that reason there is a negative change. If total N2 number of particles, you can also write down N2 by TSP. Then what is TSP? N2 already you know that what is the number of particles or number of populations of higher energy state E2. Then what is TSP? TSP is lifetime spontaneous transition lifetime. Spontaneous transition lifetime. Spontaneous transition lifetime means what is the total time taken by all the particles present in the higher energy state to go back to the lower energy state or ground state. The total time taken is said to be lifetime, and this is spontaneous process, so it is said to be spontaneous transition lifetime. Clear? So rate is equal to minus dN2 by dt, or you can also directly write down N2 by TSP. Similarly, here also you can write down rate of spontaneous emission directly proportional to N2. Only N2. Only N2. Does not depend upon energy because we are not giving any external energy here. So you can directly write down rate of spontaneous emission equal to some constant A, and the particles are moving from 2 to 1, from higher energy state to lower energy state. So 2 to 1, N2. We compare equation 1 and 2. Here you can see N2 by TSP. Here we get 8 to 1 N2. So you can directly write down 8 to 1 equal to 1 by TSP also. So where 8 to 1 is known as Einstein's coefficient of spontaneous emission. Next one is stimulated emission. Stimulated emission, from the name also you can identify that we are going to stimulate the particle to start the emission process. In E2, all the excited particles are there. If one excited particle is there in E2 and again we are giving some h new amount of energy. So this much of energy is responsible to stimulate the particle to release energy quickly and convert to ground state. In excitation process, we know that particle in ground state absorb energy, go to the higher energy state. In de-excitation process, the particle in higher energy state release energy, comes back to ground state. But here it is stimulated emission. Stimulated means when we stimulate from the outside, we are giving some energy to trigger the de-excitation process or energy emission process. So externally we are giving h amount of energy. So externally when we are giving h amount of energy, then the particle will jump from higher energy state to lower energy state with the release of energy h nu. H nu energy we have given. Again external energy h nu is there. Symbolically we can write down a star is there, excited state, plus we are giving h nu amount of energy. This will release energy, so 2h nu. This is the symbolic representation of it. 2h nu because excited means some extra amount of energy is there, and again we are giving h nu amount of energy, so total energy will be 2h nu. And rate of stimulated emission is nothing but it depends upon, directly you can write down, it depends upon energy as well as how many number of particles present in the higher energy state, that is n2 and energy state, because we are giving external energy. So you can directly write down rate of stimulated emission. If it is proportional, some constant will be there, and stimulated emission means the particles are moving from higher to lower, that is from energy state 2 to energy state 1. So you can directly write down n2 rho p. This is the expression for rate of stimulated emission, where B21 is a proportionality constant which is known as Einstein's coefficient of stimulated emission. Again I am repeating the difference between spontaneous emission and stimulated emission, that in spontaneous emission all the particles are always in the excited state, so by their own they release energy and come here to ground state. But in stimulated we are giving some external energy in order to stimulate or in order to trigger that process. So when externally we trigger the stimulation process or emission process, that is said to be stimulated emission process. And A and B are always known as Einstein's coefficient. So B21, B12 and A21, all these are Einstein's coefficient. Always remember, here we have written B21, that is the particles are moving from 2 to 1. B symbol you can see, B is used when energy is involved. Here you can see we have used A to 1 means particles are moving from 2 to 1, higher to lower, but since there is no involvement of external energy, we have used symbol A. And in first case, absorption case, here B12, again energy is involved here. Since energy is involved, we have used the symbol B, and here the difference is 1 to 2, because the particles are absorbing energy and moving to the higher energy state. So we discussed about all the Einstein's coefficients. Now we have to find out the relation between all the Einstein's coefficients. So in thermal equilibrium, total number of particles moving from lower energy state to higher must be equal to total number of particles moving from higher to lower. So total absorption must be equal to total emission. If E2 and E1, if 5 number of particles are moving from lower to higher in the absorption process, then maximum number of particles moving from higher to lower will be 5. So total number must be same, but we know that absorption process is 1, but emission is 2 different types. One is stimulated plus another is spontaneous. So in thermal equilibrium, that is when temperature remains constant, that is said to be thermal equilibrium. When absolute temperature remains constant, in that case we can write down total number of particles moving from lower to higher is nothing but the absorption, which is nothing but the rate of absorption, and must be equal to sum total of rate of stimulated emission and rate of spontaneous emission. So rate means we can directly write down rate of absorption equal to rate of spontaneous emission plus rate of stimulated emission, where rate represents number of particles moving from one energy state to another energy state per unit time per unit energy. So for absorption process we have written B1 2, because 1 to 2 the particles are moving from lower energy state to higher energy state, number of particles present in the lower energy state, and it depends upon energy. For spontaneous emission there is no involvement of energy, so we have written the constant as B. 2 to 1 means since emission the particle move from higher to lower and depends upon number of particles present in the higher energy state. Plus stimulated means again B21. Here is the difference. This is B12. Particles are moving from lower to higher. Here particles are moving from higher to lower, and involvement of energy is there. So rho. So this is the equation we get in thermal equilibrium. Now we have to rearrange this equation in order to find out the relation between B12, B21 and A21. So we have B12 rho N1. If we take that B term, this term to left hand side, this will be negative, minus B21 minus B21 into rho equal to A21 into, again if we rearrange like this, B12 N1 minus B21 N2 equal to A21 N2. Now we can write the expression for energy density. If we divide this term, we get energy density. So A21 N2 divided by B12 N1 minus B21 N2. This is the expression for energy density we get. Again we have to rearrange. If we divide both the terms, the numerator and as well as the denominator, if we divide both by same factor, numerator is divided by x, denominator is divided by x, so the result will be same. There is no change in the result. So now we have to divide it by B12 N2, here also B12 N2. So we get energy density equal to, here you can see N2 N2 we can cancel. So in numerator we get A21 divided by B12 whole divided by, this term is divided with first term, so B12 we can cancel, remaining part will be N1 by N2 minus, here N2 N2 can cancel, this will be B21 divided by B12. Equation number next. But we know that N1 and N2, N1 and N2 are nothing but the populations, that means the number of particles present in energy state E1 and energy state N2. From Boltzmann equation, we know that number of particles present, number of particles, that is N. If N is number of particles present per unit volume in an energy state having energy E, then N equal to E to the power minus E by KT. This is the expression for number of particles. N equal to E to the power minus E by KT. This is exponent, E corresponding to energy of that state, capital E, K and T. K is Boltzmann constant and T, capital T is absolute temperature. So we can use that here. So for first energy state we can add on N1, so this will be E1. For second energy state we can add on N2, which is equal to minus E2 by KT. E1, E2 are different, K is a constant, T is constant, because we are considering thermal equilibrium. Thermal equilibrium means temperature must be same. E1 and E2 both energy states are having same temperature, or throughout the transition of particles temperature is maintained constant, so T is constant. Now we require N1 by N2, so if we divide N1 by N2, this will be E to the power minus E1 by KT divided by E to the power minus E to the power minus E2 by KT. Again we can write like this, negative. If we go to upper side, this will be positive. So E2 minus E1 by kT, but E2 minus E1, but E2 minus E1 is nothing but energy density. So we can write down N1 by N2 equal to E to the power h nu by kT. Here you can see N1 by N2 we get E to the power E2 minus E1, but this difference is nothing but h nu. H nu is the energy difference between energy state 1 and energy state 2 by kT. So we get N1 by N2 equal to E to the power h nu by kT. Now we are going to use that value in equation number 1. So in place of N1 by N2, here we can use that value. So you will get energy density equal to, using in equation 1, we get energy density rho equal to, see here, numerator we have A21 by B1. We can directly write A21 by B1 divided by, here we have N1 by N2. In place of N1 by N2 we can write down E to the power h nu by kT minus, here you can see B21 by B12 is there, so directly you can write down B21 by B12. So this is the derivation we get for expression for energy density. But from Planck's equation, we have the generalized form of energy density as 8 pi h nu q by cq, 1 by e to the power h nu by kT minus 1. So this is the general equation for energy density corresponding to an energy state. So here we get energy density equal to this from our derivation. This is the standardized equation. If we compare that, here you can see A21 B12, but in place of A21 B12 in the original equation we have this. So directly we can write down A21 by B12 equal to 8 pi h nu q by cq. If you cross multiply, you will get the relation between A21 and B12. Again, in denominator we have e to the power h nu by kT minus B21 by B12. Here we have e to the power h nu by kT minus 1. So in place of B21 by B12, we have here 1. So you can directly write down B21 by B12 equal to 1. That implies that B21 equal to B12. So this is the relation between Einstein's coefficient, and this derivation is important for your exam. So prepare well for this equation. Okay? B12 by B2. Next we have one term, population inversion. Inversion means opposite, and what is inversion here? The population. Population is nothing but how many number of particles present in an energy state. So N1 and N2 are nothing but the number of particles present in E1 and E2 corresponding to energy states. So those N1 and N2 are said to be population. So population inversion means in original state or in stable state, or you can say in thermal equilibrium, always you will find out more number of particles present in the lower energy state as compared to higher energy state. So always if you plot a graph, then you will get, always you will find out more number of particles here. This is N1, N2, N3 corresponding to energy state E1, E2 and E3. Always you will get N1 is greater than N2 and greater than N3, where now in thermal equilibrium. In thermal equilibrium, you will get more number of particles present in the lower energy state as compared to higher energy state. But when for excitation process, when they get some energy, they will move to higher energy state. So the state in which we get more number of particles present in the higher energy state as compared to lower energy state, that state is said to be population inversion. So in population inversion, we get more number of particles present in the higher energy state, that is N3, N2, N1 corresponding to energy E1, E2 E3, then here we will get N3 is greater than N2 greater than N1. So the state or the condition in which we get more number of particles present in the higher energy state as compared to lower energy state, that state is said to be population inversion. And the process in which all these particles are transferred to higher energy state to get population inversion is known as pumping. Pumping is the process in which particles are moved from lower to higher energy state. This is known as population inversion. Then we will go to Ruby ledger. Okay. In our syllabus we have Ruby ledger. So Ruby ledger, this is the first ledger which is made in 1960. First ledger developed in 1960. This is a solid state. That is the material used here is solid, because ledgers can be solid, ledger can be gaseous, semiconductor, all these things. So this is a solid state ledger, and it is a 3-level ledger. What is 3-level then? 3-level means when 3 energy states E1, E2 and E3, 3 energy states are involved in transition of electron or transition of particle. That is said to be 3 energy states or 3-level. If 4 energy states are used, E4 is also involved in transition of electrons or transition of particles and in ledger action. That is said to be a 4-level ledger. So 3-level means when 3 energy bands are involved. 4-level means when 4 energy bands are involved in transition or in ledger action. So Ruby ledger is a 3-level ledger, solid state ledger, and developed in 1960. So it contains a ruby crystal along with aluminum oxide doped with chromium ion. So doping, I think you already know, doping is used in order to increase the conductivity, because more number of conducting particles or ions are there. So it contains ruby crystal, aluminum oxide doped with chromium ion. So the doping percentage is 0.05 weight percent. 0.05 weight percent. That is what is the total weight of the particles, and we are considering only 0.05% of total weight in order to calculate the doping percentage. Then with concentration of doping about 1.6 10 to the 25 number of chromium ions present. So these ions have a set of 3 energy levels. Since 3 energy levels, this is said to be 3-level ledger. When 3 energy levels are involved, that is it has to be 3-level. When 4 energy levels are involved, that is said to be 4-level ledger. Then we will go to the working, construction and working. Here you can see the construction. So it contains a ruby rod. This is a ruby rod. So both sides you can see here. So one of the side is completely polished, other side is partially polished, and the size of this ruby rod is in the range of 4 centimeter in length and 0.5 centimeter or 0.5 centimeter in width. And this ruby rod is placed parallelly or along the axis, and you can see here, you can see xenon flash tube is there. So xenon flash tube is surrounded in spiral around that ruby crystal, from which it will get energy. So when switch is on, then xenon light falls on the ruby crystal, and this light is sufficient to excite the chromium particles present in the lower energy state to go to the higher energy state. So directly they will go to the third energy states, because the wavelength of xenon light is 5500 angstrom. So energy is nothing but equal to h nu. So hc by lambda. So if you put the values of hc lambda, you will get the energy. That much of energy is sufficient to move the particle from directly E1 to E3. And here you can see coolant is used, because when light falls it will get heated, so in order to cool down, coolant is used. So this is the structure which is explained here. Here you can see 4 centimeter in length and 0.5 centimeter width. One end is partially reflecting, polished, and one end is fully reflecting. Along the axis they present. Then helical or spiral photographic flash lamp is used, which is made up of xenon. So xenon wavelength, remember, 500 angstrom. So this xenon flash produces white light, and which activate the particles move from lower energy state to higher energy state, and coolant is used in order to cool down. Then the working principle. The working principle means when general light falls on that particle where present in the ground state or E1, then here you can see the wavelength of general light is represented. So this amount of light is sufficient to move the particle from E1 to directly E3. And in E3, they are higher excited state means they are unstable. So E3, due to unstable nature, they lose some energy due to collision and slightly comes back to E2. This is E2, and E2 is always, remember, a metastable state. Metastable state means where they stay for a longer period of time. So over the time, you will find out more number of particles present in E2 as compared to E3, as well as from E1 also. So population inversion takes place between E2 and E1. So from population inversion when it takes place, one particle jump from E2 to E1 by releasing 6943 angstrom of energy. So this is the wavelength corresponding to E2 and E1, 6943 angstrom. So this amount of energy is spontaneous emission, not stimulated. But this energy stimulate other particles present in E2 to release same amount of energy. As a result of which, when intensity increases, we get laser here. Highly intense light we get, whose wavelength is 6943 angstrom. This is known as laser action of ruby laser. You can see radiation of 5500 angstrom falls. So directly they move to E3. Here again the complete working is written here. You can go through that. So now part of intense light, when sufficient amount of light get and intensity increases through the partially reflecting surface, they release and we get laser. This is the working of ruby laser. Then applications, nowadays laser are used in day-to-day life, you can see. So here are the applications: optical fibers communication, cutting and welding of metals in medical field, then vaporization of unwanted material during manufacture, different important purpose in medical and defense, CD drive, then task in thermonuclear reaction. These are the applications of laser. So go through the applications. In next video, we will discuss about optical fibers. Thank you.